today we're going to finish up this topic, and then I'm hoping that the timing works in such a way that we'll finish this up, we'll take a break, and then we'll start the next topic. And I have all the notes for that. So I realized that I had one other thing that I wanted to talk about regarding the example that we did last time. So we're going to do that to start. So just to remind you what this example was, we were looking at finding, what were we looking at finding? We were looking at the power, we were trying to find the power input to this pump. That's essentially a well pump that brings water down from a pretty long distance under the ground up to presumably a house. All right, so we used conservation of mass and energy, as well as applied some of the simplifying assumptions that we talked about making for these types of turbo machines, simplified our equations, and then we're able to work out what the work was required for the pump input. All right. The other thing that I wanted to note on this problem is the following. So friction can also be a very important factor in these types of systems. We ignored that, right? So friction is generally a loss in your system. And so it's very possible that the pump you would actually need for this system should be much larger. But the issue of friction is something that we talk about in 3500, so I'm not going to talk about it in this class, but I wanted to bring your attention to it. So friction is a source of losses or inefficiencies in these types of systems. So the pump that might actually be needed could be much larger. Or this pump might require more power. Okay, so more detail on this in ME 3500. If you're an ME student, you will see that eventually. Okay. But another follow-up question that we might ask is, what is the pressure rise across the pump? All right, so our pump, we're going to draw as a circle, and we have our inlet and our outlet. And we have work going into this thing, right? Okay, so my control volume is just the pump itself. All right, and I already have from before our conservation of energy. Is just 0 minus W dot CV plus M dot HI minus HO. All right, so I'm just replicating our conservation of energy with all the simplifications that we made before. If you remember that W dot CV is equal to work out minus work in, then that means that we have positive W dot in plus M dot HI minus HO. All right. And what we're going to do to find the pressure drop is we are going to recall that HI minus HO is equal to the specific heat times the temperature difference plus the specific volume times the pressure difference. All right, so I'm going to substitute this into my conservation of energy equation. But before I do that, I'm going to make a note that if you remember, the temperature coming in and out of the pump, we're assuming is the same. So this goes away. No temperature change. All right, so our equation then becomes that 0 is equal to W dot in plus M dot heat capacity, oh, not heat capacity, specific volume times P out minus P in. All right, so if we want to find this, we're just going to solve for it. And so we have PO minus PI is equal to minus W dot in divided by M dot times specific volume. All right, so we have all of that information and we can plug it in. So we have minus 13 horsepower over 33.34 pounds of mass per second times 0.01604 cubic feet per pound of mass times a conversion. So I have 550 feet times pounds of force per second is equal to 1 horsepower. And then I also need to convert 1 foot is 12 inches and 1 PSI is 1 pound of force. 1 pound of force per square inch. All right, so we get that the horsepower cancels. We have, oops, this should be quantity squared. Sorry about that. We have pounds of mass canceling. Per second cancels. Pounds of force cancel. Our square inches cancel. And our feet. Oh, yes. Okay. So we have feet squared times feet is feet cubed and then divided by feet cubed. So this all gives us PSI in the end and we get 92.85 PSI. Okay. Sound good? Okay, cool. Yes. Yes, this is specific heat. So just to recap, because it feels like it's been a while ago to me, so it must feel like that to you as well. Specific heat, we just use one value for incompressible substances, which liquids are, and water is incompressible. So CV and CP are the same, so we just call it C. All right, you would find this in the table. Okay. Okay. Now let's talk about another steady flow device. This one is called a throttling valve. And this is any kind of flow restricting device that causes a significant pressure drop in the fluid without any work input or output. All right. So some examples include adjustable valves, capillary tubes, and porous plugs. The pressure drop that we get is often accompanied by a large drop in temperature. So these devices are commonly used in refrigeration and air conditioning applications. Okay. As we've done with all the other devices, let's talk about the relative importance of the terms that we have in our energy equation. So this should be 4 throttling valves, and so it is the following. So we are still assuming that this is a steady flow device. So that means that this term goes to 0. So when we have steady flow, we have no time derivatives. We're also going to assume that Q dot is approximately 0 because the heat transfer area is small. All right, so I'm going to take out this one. By definition, W dot is going to be 0. So these systems don't use or make work. So we get rid of that. And then for arguments that we've made before, our change in potential energy and our change in kinetic energy are going to be assumed to be very small relative to the change in enthalpy. Okay, so we'll get rid of this term as well as this term. Okay, so our energy equation then simplifies to just 0 is equal to m dot times hi minus he, or that enthalpy is equal at the inlet and the exit. Okay. So on a curve of T versus H, so just like how we did TV and PV diagrams, we can have the horizontal axis be enthalpy. So in these devices, what the process from going from the inlet to the exit is going to look like is the following. Oops. Inlet to exit. Inlet to exit. All right, and so you'll notice that depending on what state you're in, the delta T is going to be smaller or bigger, okay? One more note. So what happens when the fluid is an ideal gas? So H is only a function of temperature for ideal gases. So if we have that HE is equal to HI, then what does that mean about TE and TI? They also have to be the same, right? So for an ideal gas flowing through a valve, we have that the inlet and exit temperatures and the inlet and the exit enthalpies have to be the same. Okay. So this is only for an ideal gas. Okay. Another device that is common in engineering is a heat exchanger. This is a device that transfers heat between two fluids at different temperatures. So these are used pretty widely, and they come in a lot of different configurations. So this first one, we have a fluid coming in the top and then another fluid passing through this bottom pipe. This is a direct contact or mixing chamber heat exchanger. So this is sometimes referred to as an open feed water heater. All right, so our top fluid is coming in and then our side fluid is coming in and they both mix in this big tank that's in the square. Okay, so the fluids are in contact with one another, and then in the outlet, it will have a different temperature than both the top and the inlet, both of the inlet temperatures. Okay. The second one is a double tube. Or a tube and shell counterflow. Heat exchanger. These are sometimes called recuperators. All right, so here the fluids don't touch each other. They don't mix. They're completely separate. So we have our fluid A coming in this pipe and leaving, and then our fluid B is coming in through this chamber and then coming out the other side. All right, so the heat transfer is going to happen like through the walls of the tube in the middle. Okay. All right. We can also have that same idea as image B, but when the flow is not counterflow to each other. So this one is a double tube heat exchanger as well, but this is a parallel flow configuration. We talk about heat exchangers quite a bit in 3500 as well. So the differences between the different counter and parallel flow configurations are talked about more in that class. And then last but not least, we also have a cross flow heat exchanger. So an example of this would be your car's radiator. Okay, so in most of the heat exchangers, the fluids do not mix. So conservation of energy, I'm sorry, conservation of mass is given as the following. So we have mass flow rate of the cold coming in is equal to the mass flow rate of the cold coming out, or is just m dot of cold. All right, and then similarly, we have the mass flow rate of the warm fluid coming in is equal to the mass flow rate of the warm fluid coming out, which is just m dot warm. So W equals warm, C equals cold. And this is for when the fluids don't mix. So when you have a mixing chamber heat exchanger, like is shown in the top one to the left here, and this is also how a shower head exchanges heat, the conservation of mass is a little bit different. So that is going to look like the following. So we have dm dot cv dt is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out. We're still assuming that this is steady, so we can get rid of this. But now we have to be a little bit careful with our inflows and our outflows, okay? So in this case, we have, should be coming in. So we have our hot water stream coming in, and then our cold water stream coming in, and then our final mixed temperature coming out. So in this case, we have 0 is equal to m dot 1 plus m dot 2 minus m dot 3. Okay. Okay, great. Okay, so let's talk for heat exchangers about the relative importance of the terms that are in our energy equation. So we have the following. So if for Q dot, it will depend on what we're considering. So if the system is the entire heat exchanger, then Q dot for our control volume is roughly 0. So we're going to assume that our heat exchanger unit isn't exchanging heat with our surroundings very well. We're basically making an assumption that it's well insulated. So that is this circumstance. All right. However, if Q dot for CV, if the system is just one of the fluid streams, then our heat transfer is obviously not 0 anymore, right? That's the whole point of this device, is that we're exchanging heat with the other fluid. All right. So if our perspective is that we're just looking at one of the fluids in this heat exchanger, then we will of course have to keep Q dot. All right. And so that's this system. Okay. W dot. So our rate of work, we're going to assume is generally 0. So the heat transfer is just happening because of the fluid coming in, the two different temperature fluids coming in contact with each other. We're also going to neglect kinetic energy and potential energy for the same reasons as we have before. All right. So if we make these simplifications, so our work term goes away, our kinetic energy term goes away, and our potential energy term goes away. And then we're still assuming that we're looking at steady systems. So then our energy equation simplifies to the following. So there's two circumstances, right? So if the control volume is the entire heat exchanger, we can get rid of that Q dot term. So we just have that 0 is equal to the sum of m dot I hi minus the sum of m dot E he. And in scenario number 2, actually, let me write this out a little bit more. So if we have, so for the 2 fluids, I'm going to call them A and B. This equation becomes the following. So we have m dot A HA at the inlet plus m dot B HB at the inlet minus m dot A HA at the exit plus m dot B HB at the exit. Okay, and this is obviously assuming that we have an inlet for each fluid A and B, and then an exit for each fluid A and B. Okay. All right, so if we have the control volume is just the working fluid, so if CV is just fluid A, then we would have 0 is equal to Q dot of our control volume plus m dot A HA inlet minus HA exit. Okay. Make sense? Okay. Let's do an example. Perfect timing. We'll do this example and then we'll take a break. I love it when a plan comes together. Okay. So we have refrigerant R134A is going to be cooled by water in a condenser. The refrigerant enters the condenser with a steady mass flow rate of 6 kilograms per minute at 1 megapascal and 70 degrees C and leaves at 36 degrees C. The cooling water enters at 300 kilopascals and 15 degrees C and leaves at 25 degrees C. Neglecting any pressure drops, determine the required mass flow rate of the cooling water. Okay, so let's talk about what we should do. So let's write down what we have. So we are given several things. So the pink is R31A or R34-1A. So I'm going to put all of our refrigerant stuff in pink text so we can keep ourselves straight. So we know that R134A inlet conditions are the following. We have m dot is equal to 6 kilograms per minute. P inlet is 1 MPa. And then T at the inlet is 70 degrees C. All right, and then for the exit, we have the following. So again, our m dot is 6 kilograms per minute. And the temperature at the exit is 35 degrees C. No, it should be 6, right? So this should be a 6. What? That's what's in the problem in the text. I just had a mistake typo in the figure. Sorry. Okay. And then the water, I'm going to write in blue. So our water inlet and our water exit, we have that the water enters at 300 kPa. So we have pressure at our inlet is 300 kPa. And the temperature at our inlet is 15 degrees C. And it's leaving at temperature of 25 degrees C. All right, so we've got water and water. Okay. So our first question is and we want to neglect any pressure drops. So this means that our pressure entering and leaving is the same. So this means that PE is also 1 MPa, and then PE for the water is 300 kPa. Okay. Okay, so the first thing that we want to find, well, the only thing that we want to find is m dot for the water. So find m dot for the water. Okay. Okay, so the first thing that we're going to do is we are going to choose a control volume. When we're looking at conservation of mass, what we're going to do is we're going to choose a control volume for R134A, and then also a control volume for the water. Okay, so our step one is apply conservation of mass to each fluid separately. All right, so I am going to, oh, these are already labeled. So we have for our refrigerant, so for this control volume, we have that the time rate of change of mass flow rate of mass in the control volume is equal to the sum of the mass flow rate at the inlets minus the sum of the mass flow rate at the exits. We have one inlet and one exit, and this is steady. So this is 0 since it's steady. And then we have one inlet and one exit. So what we have here is that 0 is equal to m dot in minus m dot e, which m dot in is m dot 3 and m dot exit is m dot 4. Okay, so we have m dot 3 minus m dot 4, which just means that the inlet mass flow rate is equal to the outlet mass flow rate, which is just m dot, which was already given to us as 6 kilograms per minute, right? So that's not very exciting. We already kind of knew this, right? Let's talk about for the water. So we have the same kind of governing equation here. So my control volume is going to be everything except for the R34A. So I'm just drawing my control volume to include only the water. All right, and we have the same simplifications. So we still end up with 0 is equal to m dot I minus m dot E. For the water, our inlet stream is m dot 1, and then our outlet stream is m dot 2. So we have 0 is equal to m dot 1 minus m dot 2, which means that m dot 1 is equal to m dot 2, or just m dot W. Okay, so we've used conservation of mass to tell us that there's only one mass flow rate that we have to be worried about for the water. We don't have to worry about m dot 1 and m dot 2 individually. It's just the same thing, right? Okay, so that's good. So now we want to use our conservation of mass, but we're going to apply it to the entire heat exchanger. So we're going to apply conservation of energy to the entire heat exchanger. Okay, so we have the time rate of change of the total energy in our control volume is equal to Q dot CV minus W dot CV plus the sum of the inlet energies. So we have enthalpy plus kinetic energy plus potential energy, and then minus the energy flowing out at the exits. So again, we have enthalpy, kinetic energy, and potential energy. Okay, we're going to simplify this because we know a number of things. So this is steady, so we can get rid of that. We're going to also assume that our heat transfer can be approximated as 0 since we're looking at the full heat exchanger. What color did I use for work? I don't remember. There's no work produced by the system or done to the system, so we can get rid of that. And then we're also going to get rid of our kinetic energy and our potential energy because we're arguing that they are small relative to enthalpy. Okay? So we have 0 is equal to m dot I times HI minus the sum of the exit m dots times enthalpies. Okay? Okay, so we have all the tables in here, and you have a page for writing. I'm just going to move this up a little bit so I don't have to. There, okay. All right, so we have 2 inlets and 2 exits, right? Our inlets are the following. So, oops, this should be an I. So our inlets are m dot 1, enthalpy at 1, plus m dot 3, enthalpy at 3, minus m dot 2, H2, plus m dot 4, H4. Now just remember, 1 and 2 are water, and 3 and 4 are refrigerant, okay? All right, I want to make another simplification. So remember when we did our conservation of mass, we had m dot 1 equals m dot 2 is m dot water, and m dot 3 equals m dot 4, which is m dot R. I don't think I called it m dot R before. Let me fix that. So let's call that R for refrigerant. Okay. So I can rewrite this equation. So I'm going to group the water terms together, and I'm going to group the refrigerant terms together. All right. So I have that 0 is equal to m dot water H1 minus H2 plus m dot refrigerant H3 minus H4. Feel okay for everybody so far? Okay. We already have m dot R, and we can find all these enthalpy values in the tables. And all that's left to find is this. Okay, so I'm gonna solve this equation for m dot w, where we have minus m dot r h3 minus h4 divided by h1 minus h2. Okay. And then we're going to use our tables for each of these enthalpy values. So let's do water first. And we're going to use, we're going to use table A4. So H1, we're going to use that we have the temperature at 1 is 15 degrees C, and we have that P1 is equal to 300 kPa. All right, so first we want to figure out what state we're in, right? So let's look up the saturation pressure. So Psat at T1 is this guy here. So we have 1.7057 kPa. All right, so our pressure at 1 is much larger than our saturation pressure. So that means that we have a compressed liquid, right? So I don't have that table in here for you, but we are going to approximate our enthalpy at 1 as the saturation enthalpy at temperature 1 for a saturated liquid. And so we're going to go back to the same table to get that. So we have this value here. All right, so we have 62.982 kilojoules per kilogram. All right. And then H2, so at the exit for the water, we have that the temperature is 25 degrees C and the pressure is still 300 kPa because we're neglecting any pressure differences. So now we need to compare again to the saturation pressure at T2. So we'll go back to our table and look at 25C. So we're here. So 3.1698, which again is, we're at a much greater pressure than the saturation pressure at that temperature. So this is a compressed liquid again. Right? And so we're going to do the same thing for H2. So we're going to assume that it is approximately the same as the saturation liquid enthalpy at T2. So we'll pop back over to this table and we'll grab this value. So we have 104.83 kilojoules per kilogram. Okay, so we got water sorted. Alternately, we could have done the following. And actually, I think, Josh, was it you that asked me this? I think you asked me a similar question about homework, kind of along these lines. So we could have alternately said, well, we know that H1 minus H2 is equal to the heat capacity times T1 minus T2 plus the specific volume times P2 minus P1. We have no pressure change, so we can get rid of that. And then we could have calculated this enthalpy difference as the specific heat times the temperature difference. So we would have just had to look up C. I believe, I don't have the table replicated in the notes for you. C doesn't change a lot with temperature for water, like in a narrow range. But the kind of the downside of doing this way is if there are differences in the heat capacity for water at 15 and 25 degrees C, you'd have to take an average. So then this enthalpy difference would be slightly less accurate. Okay. So if you can use the table, that would be preferred, but you can do this as well. Make sense? Okay, cool. All right, now let's repeat this process, but for, oh, I shouldn't have done that in pink. Oh, well, okay, sorry. I had a whole theme. So I'm gonna just highlight this. It goes with the water discussion. Okay. So for our 134A, we're gonna do a similar process. So at T3, we have 70 degrees C, and then P3 is 1 MPa, which is 1,000 kPa. So we want to figure out what the saturation pressure is at T3 to figure out what state that we're in. So we will go to our saturated R134A table. So it's the same thing as what we have for the water tables. It's just for this different fluid. So we are going to go to 70 degrees C, which is here. And our saturation pressure is 2,118.2 kPa. So we are sitting at a lower pressure than the saturation pressure. All right, so this means that we have a superheated vapor. Okay, so we will go to table A13, which is right here. And we first want to find our pressure cell. So we are looking for 1 MPa, which is here. And we have 70 degrees C. So we're going to go over to look at this line. So we're going to be looking at these values. And so our enthalpy is this guy right here, 303.87. Kilojoules per kilogram. And then now let's look at T4. So we have 36 degrees C, and then P4 remains at 1 MPa, which is again 1,000 kPa. So we want to look up our saturation pressure at T4. So let's go back to this table. So we're now at 36. All right, so our saturation pressure is 912.35 kPa. So we are above our saturation pressure. So this is a compressed liquid. All right, so we'll use table A11. So that's our saturation table. And we are going to approximate H4 as being the same as the saturation enthalpy for a saturated liquid at T4. So we will go here. So here's our saturated refrigerant table. At temperature of 36, our enthalpy is here. So we've got 102.34. kilojoules per kilogram. Okay, so now we're just gonna pop all of that information into our m dot equation. So we have our minus 6 kilograms per minute times 102.34. Nope, sorry, that one comes second. So we have H3 minus H4. So we have 303.87 minus 102.34 kilojoules per kilogram, and then divided by H1 minus H2. So we have 62.982 minus 104.83 kilojoules per kilogram. And we get 28.9 kilograms per minute. Does that feel okay to everybody? One small note, so we have a minus sign out front, which would be alarming if we had a negative mass flow rate, right? So we end up with a positive value for the 303.87 minus 102.34, but then in the denominator, we have a negative sign because we have the 62 minus 104. All right, so that's how we get our positive mass flow rate.